All right, ready to dive in. We're tackling a big one today, a question that's kind of haunted, well, everyone forever.
Yeah.
What is reality really made of? I mean, we've all wondered it, right?
Right. Yeah.
And you especially have been digging into some seriously cool stuff on this looped quantum gravity, right?
It's a wild ride, this one.
It really is. But before we journey into the quantum foam or whatever, let's set the scene for folks.
Okay.
You've been looking at different theories, like string theory, where everything's, what, tiny vibrating strings?
Right. Yeah. That's the gist.
So, just for fun, physics showdown, which theory has the cooler name? I'm going string theory sounds way cooler.
Uh-huh. Yeah. It's catchy. I'll give you that.
Mhm.
It's going for that whole theory of everything vibe. Wants to explain it all.
Right, right.
Forces, particles, the whole shebang.
Ambition.
Totally. But loop quantum gravity, LQG, if you're feeling cool,
I like it.
it's more focused, like laser focus on one huge E problem, gravity.
Which, let's be real, is kind of important.
Kind of. It's holding the entire universe as we know it together.
True, true.
Stars, planets, why we're not just floating off. Kinda key.
More than kinda, I'd say. And from what I've been reading, LQG isn't just explaining gravity, it's like challenging Einstein himself.
It's true.
Bold move.
It really is. One of the most fascinating things about LQG is this idea that the speed of light, something Einstein considered untouchable, might not be so constant after all.
Okay, wait, hold up. Even I know that's a big deal. Nothing's faster than light, right?
Right.
How could it not be constant?
This is where it gets really interesting.
Yeah.
So picture this. LQG says space-time at the tiniest level isn't smooth.
Mhm.
It's grainy, like quantized, almost like it's made up of tiny interconnected loops.
Okay.
This graininess could actually make the speed of light vary, just slightly, depending on the light's energy.
Real?
Yeah, it's called Lorentz invariance violation.
Catchy.
Right, and it's a huge intimation of LQG when physicists are really trying to test.
So instead of like a smooth racetrack where light always goes the same speed, it's more like bumpy. Light speeds up or slows down depending on its energy.
Exactly.
Whoa, this isn't just like light being a bit faster, it's changing how we understand space and time entirely.
It's a whole new way of looking at the universe.
Mind-bending for sure. And speaking of, you know what else this LQG stuff reminds me of? Legos.
How so?
Well, remember string theory with the tiny vibrating strings? LQG has its own building blocks for reality, but instead of strings, it's these super tiny interconnected loops making up space-time itself.
And when we say tiny, we mean unimaginably tiny. Think billions of times smaller than an atom.
See, now I need a visual aid because atoms are already tiny.
Right,
This is like the Lego instructions are in a language we don't even know.
pretty much. Building the most complex Lego set ever, in the dark, not even sure you have all the pieces.
So how do physicists even start to test a theory like that? We can't shrink down to loop size and watch.
Not yet, at least.
You're right.
But that doesn't mean we're totally clueless.
Okay, good.
There are ways to look for LQG's fingerprints on the universe. Remember those gamma ray bursts we talked about?
Those crazy, powerful explosions,
Mm.
right?
Exactly. They might hold the key to testing LQG.
Wait, really? How so?
Well, think about it. Gamma ray bursts, most energetic things out there, traveling huge distances across the universe.
Okay, I'm following.
LQG says those tiny variations in light speed, the ones in the grainy spacetime, they would add up over those huge distances, like running a marathon on that bumpy track.
Yeah.
It's going to have an effect.
So the idea is, if we can observe these gamma ray bursts closely enough, we might pick up on those tiny changes in light speed that LQG predicts.
Exactly.
Oliver!
And recently, astronomers have gotten the tools to do just that, the results. Well, that's where things get really interesting.
So we've got these gamma ray bursts, like cosmic messengers, right? Carrying potential LQG clues across the universe.
That's the idea.
What'd they tell us? Did we find those tiny speed of light changes?
That's the thing. In 2022, astronomers, they analyzed this crazy powerful gamma ray burst, the most powerful one ever recorded.
No way, seriously.
Yeah. Hoping to find those variations.
Yeah.
Nothing. No variations.
Whoa. Talk about a letdown. I mean, everyone's expecting a revolution, and then bupkis.
It definitely shook things up.
Yeah.
Because even within the LQG community, not everyone was sure we'd find those variations.
Really? So it's like LQG had its own internal debate going on?
Exactly.
Some researchers were like, yep, gonna see it, and others were like, hold your horses.
Pretty much. You had physicists like Lee Smolin, super optimistic. They figured LQG was ready.
Mm-hmm.
It could make these bold predictions, like about the speed of light changing, and we could test them.
makes sense.
They were excited, pushing the boundaries, seeing if LQG could handle the spotlight.
And on the other side.
You had folks like Carlo Rovelli, one of the founders of LQG, actually urging caution.
Interesting. So what was Ravelli's take?
So he agreed LQG could allow for that speed of light variation, but he wasn't convinced it had to.
Okay.
He kept stressing how crazy complex the math of LQG is, translating this beautiful, elegant theory into actual predictions. It's hard.
It's like we've got this brand new, super advanced sports car, but no one knows how to drive it yet.
Exactly. Perfect analogy.
We know it's got potential, but actually using it is a whole other story.
And that's theoretical physics in a nutshell, especially when we're talking about stuff so far removed from our everyday world. You can have the most amazing math, but connecting it to reality, to what we can observe, making predictions we can actually test. That's the real challenge.
So even the experts are debating what LQG actually says will happen. Where does that leave us? And more importantly, where does that leave you, the listener, trying to figure all this out? You came here for answers about reality itself, and now we've got even more questions.
You know, I think that's kind of exciting. Science isn't about having all the answers right.
True.
It's about being okay with what we don't know, asking those big, crazy questions, and accepting that what we think we know might be wrong.
So even the smartest people are still figuring things out. That's actually kind of comforting.
Right. We're all in this together.
It's not a setback for LQG. It just means there's more to discover.
Exactly. Who knows? Maybe someday we'll be able to say for sure, yep, LQG nailed it, or nope, back to the drawing board.
That's the fun of it, right? The mystery.
For now, LQG is this tantalizing puzzle, this hint that there's a deeper reality out there, and we're just starting to put the pieces together.
And speaking of putting pieces together, we haven't even touched on what it would mean if LQG turned out to be even a little bit right. It's like we've been going through this intricate map of LQG, right, following the paths set out by like Smolin and Rovelli, these big names. And we get to this point, and it's like the map just stops. Big question mark about what happens next, T. If LQG is even partly true, what does that even look like?
It would seriously shake things up. I mean, imagine a universe where space and time, they're not smooth, they're not continuous, but they're built from these tiny, tiny loops. A universe where gravity itself is quantum, where even the speed of light, that could change.
We've been talking about this stuff for a while now, and I gotta be honest, it still kind of breaks my brain a little.
It's a huge E shift, no doubt.
It's like trying to picture a new color or something.
It's a whole new way of seeing reality. And the implications, they're huge. For one, black holes completely changes how we think about them.
Black holes are already so mysterious. How would LQG change things?
So right now, our best theories about black holes, they come from Einstein's theory of general relativity. But that theory, it doesn't really work with the quantum world, right?
Right.
LQG could be the bridge, the quantum gravity theory we need to finally get what's happening inside those things.
So instead of just being like points of infinite density, these singularities, LQG might actually let us see what's at the heart of a black hole.
Exactly. We might find that space-time itself, at that point, it just breaks down into those fundamental loops. It could even tell us something about the Big Bang itself, the very beginning.
Whoa, okay. So we're talking about rewriting the entire history of the universe here.
LQG has that potential, yeah.
Black holes, Big Bang, all of it. It's like LQG has the key to the biggest mysteries in the universe.
It's a powerful idea, and it shows how important it is to question everything, even our most basic assumptions. Sometimes, the biggest leaps forward come from imagining a reality that seems impossible.
It's like the more you learn, the more you realize you don't know.
Right. It's humbling.
LQG is definitely proof of that. Well, it's been amazing exploring this with you. So to everyone listening, think about this. What if our universe is way more bizarre, way more wonderful than we can even imagine right now?
What if it is out built on these tiny, tiny loops, woven together into everything we see? Keep asking those questions, keep exploring. Who knows what we'll discover?
And on that note, we'll catch you next time on The Deep Dive. Until then, stay curious.